Hello, I'm here to briefly talk about our bridge design. So we actually changed our previous design. For the first design, we used more on the wooden dowel, but we misunderstood the project brief, which we only can get 1.5 meter. So now the second design, we've picked suspension bridge. This is because it is very cheap and very easy to build. In this design, foam and string are the main material that we had used for the project.
Regarding the bridge deck, the polystyrene foams and wooden downs are applied in the structure. Generally, the properties of foams are that it has high compressive strength and low tensile strength to overcome the foam's natural weakness in tension and reduce the possibility of cracking. The wooden downs are inserted in order to reduce the tensile stress. In addition, their foam main tower are made of plywood and using the sellotape to bind the plywood member together as a pillar. This composition can enhance the softness during the loading. Finally, the supporting strings which run horizontally between the down loops, meanwhile supported by the tops of the towers. Thus, the string can carry the bridge tensile force and transfer the composition to the ground via the towers.
I am here to explain about how the bridge failed. As you can see here, only one part of the deck failed. This is because more load is concentrated on this part of the deck compared to the other part of the deck. As we all know, the wooden dowel is brittle. So when 32 kgs of load is applied on the deck, as in on the wooden dowel couldn't withstand 32 kgs of load. It buckled out of the foam, causing the deck to fail. The string is connected to the pillar. So when load is applied on the deck, the string will be under tension and it pulls the pillars inward, causing the pillars to buckle. This is also because the string is not aligned with the pillars, hence it buckled sideways.
As an improvement on the deck, the foam should be thicker. This is because when we penetrate the wooden dowels into the foam, it makes a hole. It becomes weak. So increasing the thickness of the foam make the foam strength bigger than before, so the bridge won't fail. Another point is for the pillars. So when we connect the two pillars with the horizontal strap at the top to ensure it won't back up.
We have further developed a mechanic concept to our bridge project to improve and to modify this bridge in order to decrease the chance of bridge failing. Let's see these two cases. For cable A to B, case 2 is steeper, while cable B to C, case 1 is steeper. When the same amount of load approach, tension and compression occur. The ratio of tension and compression force between case 1 and 2 is calculated, where here are the steps of calculation we have done. In case 1, we consider equilibrium in point A and B to get the value of tension 1 and tension 2. Lastly, we also calculated values of compression force. Same goes to case 2. This is the summary of comparison for two cases. From here, we can clearly see that the tension force 1 is 1.84 greater in case 1, while tension force 2 is 2 times greater in case 1 as well. Also, compression force in the pillars times 1.67 greater in case 1. Therefore, case 2 has lesser compression force, which is much more effective and economical design.
In the beginning, the bridge defected much at the first 8 kg increment. During the loadings, we can hear that there are the crack signs presented when the bridge were loaded with 4 kg to 8 kg increased. Afterward, with putting more increment, we can observe that the bridge is defected. In the observation, we can assume that the defect of the bridge is following the yarn modules. The crack sign is presented in 4 kg to 8 kg means the deck of the bridge is at the elastic limit and no longer to obey the Hooke's law at the elastic regions. Also, the fracture point is at 32 kg. Now, I'm going to talk about the failure assumption. The first one is about the buckling. Buckling is a sideways deflection of the structure is subject to the compressive stress. In our design, pillar is composed with the form of the abutment. A fixed pin function is added between the others. So therefore, the pillar towers only have one degree of freedom, which is the bending moment. Therefore, buckling occurs in the pillar. Moreover, as the applied load is increased on the pillar, the load will large enough to cause the pillar to become unstable and have buckled. For further loadings, possibly leading to complete loss of members, loading the carrying capacity and cause the unpredictable deformations. So about our bridge testing. When the bridge was loading at 32 kg, the pillar tried to buckle before it collapsed. This because when the pillar buckled, and the pillar is no longer able to withstand the force as much as before, so more loading force were gave to the deck and the deck break by over its maximum carrying capacity.